topics that other people have not looked at. It is always for the loophole in our understanding. And there is one magnificent example of that. If you were asked to define the criteria by which you recognize something that is alive, a real problem faces those of us who have contact with senior academics. you would bear in mind the criteria that we all learned in high school. The factors of respiration, nutrition, sensibility, motility, excretion. And then you would turn to the standard texts on plant physiology. And you will find, to my surprise, that the word excretion does not appear in those texts. If you look through the index, it is simply missing. If, as I have done, you look at great length through all the long books, then you will eventually find the occasional reference. And when you actually turn to the reference to the text, you will find the subject is dismissed in a paragraph. Yet plants must excrete, partly because they're alive, and therefore, by definition, they must have complex excretory mechanisms. And also because of the fact that no metabolic system exists that is not predicated by its need for excretion. The forms of excretion that are admitted include guttation, which is by definition not an excretory mechanism, because it only occurs under relatively abnormal conditions of high oxygen saturation, high water saturation of the plant, and it doesn't occur in all plants. Secondly, there is the deposition of insoluble and often non-degradable constituents in bark, which is fine for plants that have some. There is also the deposition of oxalates, which of course are common metabolic sinks in plants, in cystoliths, in, for instance, some of the aquatics. They don't occur in all the other plants. Now, I would like you to accept that as one small lecture in itself, and that is as far as my consideration of that end of the business has gone in the 1960s. Throughout the 1970s on my travels, I have always spent time in ecosystems, ranging from the tundra of the Arctic North down to tropical rainforests around the globe. And there you begin to see the fact that our simplistic understanding of the way that plants shed their leaves doesn't bear close scrutiny. When the fall comes, the plants get a beautiful colour, which entrances the eye, and the leaves fall off. And we all teach kids, well, they have to fall off because otherwise they'd be frost damage. Rubbish. A lot of plants don't lose their leaves in the fall. They manage perfectly well. So then you think, yes, okay, but they have resistant leaves, they have specially designed leaves, and therefore they don't need to drop them. That's wrong too, because they do. Evergreen plants drop their leaves the same as deciduous ones, but because they do it all the time, it's hard to tell the fact. The theories about the way in which plants drop their leaves are wrong too. Plants drop their leaves because of that abscission layer that forms at the base of the petiole. That must be wrong. A lot of plants form abscission layers and don't drop their leaves. A lot of other plants drop their leaves with no abscission layer. Some plants form them and then unform them again as ecological constraints change. Okay, so now let us look at the reasons why it is, this is the fourth basic item of the argument. The reasons why it is that plants lose their leaves anyhow. And there is in fact only one real theory that has ever been advanced to explain that. It was put forward by worker called Bonish in the 1920s or early 30s. And he said that the reason plants have yellowed leaves, plants, if you picture them like a house plant, with fresh green leaves at the top and yellow leaves further down, is because of nutritional competitiveness. The metabolic demands of the leaves near the meristem are such that they compete for inorganic inputs, and therefore the leaves lower down die off. And that, of course, is an extraordinarily easy view to disprove. All you have to do is to fertilize the plant for doing it. But in fact, it is quite plain that metabolic input and competitiveness doesn't apply. Plants lose their leaves in a preordained and systematic fashion. It isn't, as so many people say, simply a matter of senescence. In fact, if you look at the accounts of senescence in leaves, those accounts are normally based on research work done with detached leaves from living plants. Well, I don't wish to oversimplify a complex argument. If you severed a hand from a living person at the wrist and observed it over the next week or two, it wouldn't exactly accord with a good model of senescence for the rest of the person. If that is what we do with plant leaves, if you detach leaves, they yellow. They change biochemically, they change in terms of their metabolic cycles, and we say this leaf is senescent, it's induced senescence. You haven't induced senescence, you cut the damn thing off. Now, the model that I have always thought of a higher plant is that it is safe to construe it as being an organic wick. It has its roots contiguous with soil water, and through transpiration, water losses in the leaf, the water is drawn up and evaporates. If you think of a candle wick, you can see this process happening. You can see the liquefied wax rising up through the cotton wick, and the unburnt constituents deposit at the end of the wick, something like that, sooty blob. So there are 6 separate concepts. One of them reflectively observed, the candle in the apartment. One of them observed in tropical rainforests and up in the Arctic, coniferous forests. One of them stemming from speculations as a student in the 60s. And all of these suddenly, this spring, this year, fitted neatly together in my mind and gave me lots of that delightful, what would you call it, scrotum tightening frisson, which comes, to those of us who can conceive of that, I realise unfortunately this comes, which comes rarely, but which is a delightful and enticing experience when it arises. Because in fact, the reason that plants lose their leaves is because leaf fall is the higher plant's mechanism of excretion. The leaves are the metabolic power company, as it were, the distal mitochondria of a single cell tree. They are the metabolic power companies, the energy source, the energy entrapment mechanism. And in the leaf, the plant undertakes its metabolic processes. My argument is that at the end of the leaf's metabolic life, which is never long, leaves don't last long, at the end of that preordained, genetically controlled time, the leaf does not undergo senescence. This is the theory. The leaves, in fact, are now programmed to switch off because they don't excrete like animals do, and therefore the metabolic sinks residues remain within that leaf family. And at the end of the time, the leaf has been allotted for its metabolic activity. It yellows, which is nice to the eye, but then most waste products are yellow and brown. The leaves go yellow and brown because they are now acting as a repository of the unwanted and unabsorbed matter that the plant has produced as a result of its life processes. Now, that model is so exquisite that it ties together half a dozen areas of athletic interest. It also provides a model that I suppose, much to my embarrassment, ought to have widespread repercussions through educational orthodoxy. Because it fills in what is, when you stop to think of it, an enormous, gaping chasm of our understanding about the way that living organisms operate. After all, if nobody had ever realized until this moment that animals needed to rid themselves of surface nitrogen, here we have a parallel concept in plants. All these years, a tree at fall is having a ship. Those trees have been sitting there for thousands of millions of years with their roots crossed, unable to let go. At least our understanding suggests that. And of course you can at once see all sorts of very interesting little parallels that tie in. For example, if you look at beech leaves, they don't degrade in the bottom of a pond, but their metabolic wastes rarely do. But we must have evidence for what is otherwise surmised. And if I am right, then it should be possible to show that there are, as it were, excretion-dependent phenomena which are potentiated by the yellowing. In order to distinguish this, as I say, it should be distinguished from the basic idea of mere senescence. Just so happens that after a lot of diligent searching, I came across some data from Bidwell in Ontario, which I think will prove the point more neatly than any other way of doing it. Here we have the kind of thing that you would expect to happen. That is a graph. You can see the sneaky telltale trace of what is coming beneath it. That is a graph of the way in which experimentally senescent leaves behave. Just as you would imagine, over a period of a month or more, those are days across the bottom axis. Photosynthetic activity, chlorophyll content, and the amount of protein in the leaf drops off. To begin with slowly and then later faster. Now look at these. Nitrogen, carbohydrate, the respiratory behavior of the leaf, and its messenger RNA component all remain pretty steady during yellowing. And these four characteristics, in fact, increase after the leaf has been senescent for a month and shortly before it shuts off. Leaf yellowing, then, is not senescence. Leaf fall is not an accident. It is nothing to do with autumnal response or plants in the tropics that know no autumn doing so. All plants drop their leaves. And there are, in fact, some rather teasing speculations into which my mind has begun to wander. One of them is how interesting that flowering plants produce petals which then drop off. And I wonder whether the flowering plant's petals may be the excretory mechanism associated with the complex processes of ovule formation and of the formation of a seed. That ties it with observational reality too, since the gymnosperm plants, in which the alteration of generations brings about a free living entity that doesn't need therefore for excretion through the cone of say a chromatome. And they don't have petals, which they have to lose, because the next generation is self-contained and will have its own processes. Take a fern, it produces its chrysalis. Well, if there is an excretion residue there, it remains behind the chrysalis cell, and there they die. It's also interesting that tiny weedy little seeds, like grasses, shed tiny wee little brains. But look at those big gaudy flowers. I wonder whether there too you have an exclusion mechanism of the way. So that is a first public presentation, if one could call the family gathering like this public, of a view which could have widespread repercussions. It intrigues me enormously, and I only wish I had the time to work on it on a full-time committed basis. Sadly, I don't. There is a paper coming out in the Journal of Biological Education in a month or so, and I shall of course be doing some work on it. I'm not grant funded for it. It is a little hobby. It is a piece of realization at dawn, and for me it has cleared up some problems. And if it clears up conceptual problems for you, and who knows, a few dozen others, then I shall be extremely pleased and feel greatly rewarded for having sat around thinking about it. And thank you for sitting around. Yes, please.
There are trees like the ginkgo tree that tend to be able to survive in cities with very polluted air, and those are somewhat yellow leaves. Could it be that they're more efficient at removing the waste products that they absorb through the polluted air?
Yeah.
And in contrast, think of the black forest, where those trees are dying and losing their leaves. Maybe the pollution, those trees couldn't handle that pollution.
Yes, that's a very good question. I'll rephrase it. Those are very good questions. The ginkgo is a fascinating tree anyhow. Of course, its preservation in the Chinese temples by priests, but otherwise it would be extinct. It is like the Pseudopathus, the hybrid plane, a tree renowned for its ability to survive in those circumstances. And I think some plants have the same kind of natural resistance to pollutants, better than others, in the same way that we see elsewhere. Of course, the ginkgo, when it does produce those deep lemon yellow leaves which fall off, is doubtless doing its excretory a bit. And I don't doubt that is certainly the case. That was your first point. What was the second?
Well, I was thinking, comparing the two types of trees, that maybe the ginkgo is more efficient at removing the waste products that are in its trees, its leaves, and whatever, as compared to the other trees in the black forest that are not.
Yeah. You see, the Black Forest, I've visited the Schwarzwald on several occasions, looking at this acid rain problem. It's a wonderful facet of modern science, because you cannot demonstrably prove the cause-and-effect relationship between oxides of sulfur and nitrogen, and the loss to plant life and damage to buildings, and therefore nobody does do much about it. In my view, science is, forgive me, a little old man. I think science has probably had its day. There are a lot of phenomena of human and ecological significance that are not amenable to scientific tests. Human emotions, for example, are not the kind of thing that you can repeatedly test and experimentally demonstrate. And I think that science, in fact, as a methodology, is confined to certain repeatable phenomena, which may be the minority in terms of the sphere of human interest. My own view on the damage to the trees in the Schwarzwald is that it may be nothing at all to do with direct damage to the leaf laminate or assaults through the stomatal aperture. My own belief is, and no one has troubled to look at this, that it may be a shift in the microbiome. It may be that, in fact, changes in pH or changes in ionic shift are causing a cascade of effects through the mycorrhizal associations of the forest. And it could just be, in my view, that it's at the microbial end that we ought to be looking for the changes in that area. But again, the resistance to pollutants that are coming into the atmosphere is not the same as what I'm talking about. That is a kind of external means of shrugging off assault. What I'm talking about is specifically concerned, though naturally related to what you're saying, is specifically concerned with the plant's inherent
be then possible, in principle at least, to study the biochemical composition of a leaf on the tree with time, a typical leaf, and watch the buildup of expected metabolic products?
Yes. The answer to your question must be in the affirmative. In the first place, this work hasn't been done. And there are, of course, two reasons why it hasn't been done. One is that people haven't been thinking this way, so there's no impetus to look for it. Although the work, of course, could have great agricultural and even economic implications. But secondly, the reason that people haven't been looking at it is because, as I mentioned at the beginning of my talk, in the understanding that we have of plant physiology, there is no orthodox understanding of what waste products are. I did find, and this is the only place where I've ever found any reference to anything remotely connected with what I'm proposing today, but I did find in doing this literature search a reference to, in a book published in '63, I think, which spoke of alkaloids, and it said that the reason why alkaloids existed in plants was difficult to understand. Perhaps they were there as a defense mechanism to repel all borders. And then at the end of the paragraph it said, it has even been thought possible, presumably by the author, that an alkaloid might represent a metabolic sink comparable to excretion in animals. And I thought, gosh, he got so close. But whether or not, the trouble is, of course, he didn't pursue that because of the fact that he thought, well, that probably can't be the case. But it could just be that alkaloids are a metabolic sink. But how would we know what compounds to look for? Because people have never looked, apart from things like tubulose and tannin, people have never looked for these things. The only substances we do know about as being excretory sinks in plants are things like oxalates. And in fact, if you look at the work that's been done on oxalates, then oxalate levels in yellowing leaves do increase. And that is the only little piece of data that I can toss your way to say, yes, you're probably right. But there must be 20,000 others. And as yet we can't look because we don't know what they are.
It has been observed that in those cases where waste poison, that animals and insects that feed on those leaves will shoot the young ones. The young leaves become less toxic.
Yeah, that would fit very well. I thank you for that. I'll have some more on that after you, Milo. Yes?
Well, would you comment on things like kinase, terpenes, and ionophores, those waste?
It's very difficult to know. I mean, if you look, for example, at the eucalyptus oil, it's very interesting that oils from eucalyptus are so inflammable that the seeds of eucalyptus need to be scorched before they will germinate. I think throughout the genus that if you plant the seeds of the eucalyptus, they won't grow. But if you pass the flamethrower over them until they're scorched on the outside, they will. And that, of course, is a means of eucalyptus controlling potential overpopulation of an area in Australasia, and yet being ready to lie dormant until the explosive effects of a catastrophic forest fire that come about. And those ones are so inflammable, they're probably spontaneously combustible. But these residues, of course, are almost analogous to cellulose in the sense that they are potential energy reserves and yet not subject to degradation by the plant. Now, to what extent they might fit into the excretory hypothesis, or to what extent they might, in my view, simply be concerned with the end point of synthesis, I really don't know. And to what extent those two categories might be linked in a form of parallel causality, then only a lot of thought and work will be used to that. But it's a valid point that you've raised, and I'm sure it's concerned with this issue. Yes?
The answer to your question, I worked with Sir Robert Robbins, who's a national product chemist, and he linked the shikimate and acetate malonate pathway dead-end sync with plants, because the plant has to get up every morning and go to work. The sun shines, it has to wake up and start photosynthesizing.
Yeah.
It doesn't matter
fact, as you rightly say, that a plant is bound to photosynthesize even if it doesn't feel like it, means that since any plant must aim at minimal light levels for survival, then if it has maximal light levels, then the extra stuff has got to go somewhere. And I don't doubt that when plants were only microbes, that it was their desire to throw that stuff out, which of course is into the outside of the cell membrane. It gave us our first cell walls. I'm quite sure that's the case.
If your hypothesis is right, will leaves fall off more quickly with time receives more light than normal?
It ought to. It is interesting that houseplants, for example, tend to lose their leaves more slowly when they're going in the house, and this is just a physiological habit, than they do in the garden. And yes, I have wondered whether what you say is right or wrong, I don't know. But the question you raise is a key question, and one that can be quite easily looked at. And the answer ought to be yes. Of course, if the answer is no, or if the answer is sometimes, it doesn't necessarily validate the hypothesis. We are wonders as scientists for creating unworkable views. For instance, why are thistles prickly? Well, thistles are prickly so they don't get eaten to extinction. Except, what about all the unprickly plants like grass, which is much more common? And secondly, what about all the grazing animals like goats and donkeys and the food system? So we love to create meaningless hypotheses that don't stand up to critical examination simply because for the time they explain something. So that if in fact there was not a close correlation, I wouldn't be too disappointed. But the question is a good one, the observation is a key one, and I hope the answer will be in the affirmative.
Is there any particular reason to assign the eventual death of the leaf to the turning off of the leaf due to a genetic program, rather than to simply say that its capacity to store this excreted material and still function is exceeded?
Only because of the way that evolution and the way in which organisms have been known to work in the past. In other words, if that is the case, then plants will inevitably adapt to that constraint, and that is how they will have started their evolution. In other words, it's not an accident. The plant had to evolve before that mechanism was there. Mark, you have one.
In a forest, if a leaf falls and Brian Ford is not there to notice it,
I can think of no more profound points than that on which to end. Thank you very much. I shall be around at the banquet tomorrow, and it will be a pleasure to do that, especially if the second urgent assignment gets around to this very, very exciting. The second thing is that there are small numbers, a couple of dozen reprints of the extracts of both of my addresses to this meeting at the desk. There aren't anywhere near enough to go around. Extra copies can be Xerox, but please don't take them unless you would need them. But there are summaries of both of the papers outside. And thank you again. Oh, one other point. Could I invite all of you who actually have comments on the plant physiology idea to drop me a line? If you do have thoughts or ideas or pointers for data that could confirm or deny the speculation. 3 or 4 nice ideas have been put to me in the short time since I spoke. And it would be neat to have the reactions from you as to where one might go further. So if anybody does have an idea, rather than make them